To understand how some reactions happen at the molecular level, reaction mechanisms are proposed for them. The following reaction, where nitrogen dioxide gas is reacting with carbon monoxide gas to produce nitric oxide gas and carbon dioxide gas, will be used to exemplify how a reaction mechanism is created to explain how it happens at the molecular level. Scientists believe that this reaction, like many others, takes place through a number of different steps called elementary steps or elementary reactions. This reaction is believed to take place in two steps. In the first elementary step proposed, it is believed that a molecule of nitrogen dioxide reacts with another molecule of nitrogen dioxide to produce nitric oxide and this NO3 species here. In the second elementary step, the proposal is that the NO3 species that is formed reacts with carbon monoxide gas to produce a molecule of nitrogen dioxide and carbon dioxide. As can be seen in elementary step 2, the NO3 species that is formed gets consumed and does not appear as a product. It is said that such species that are formed during an elementary step and are subsequently consumed are called reaction intermediates. Their existence is transient and short-lived. This set of elementary reactions, if when added give the reaction under consideration, is called a reaction mechanism. So if you have a reaction mechanism and it consists of a number of elementary steps, and you add all the species in those steps, and it produces a net equation or a net reaction, then that is one of the criteria to show that your mechanism is valid. So if we look at these two elementary steps, let's see what species are cancelled out. This one goes, you have a nitrogen dioxide here and another nitrogen dioxide here. And what is left are these. Nitrogen dioxide reacting with carbon monoxide to give you nitric oxide and carbon dioxide. Let's see if that is same as the net equation that we had before. Yeah, exactly the same. The rate law equation for the net reaction is obtained by carrying out experiments, and it is found to be this expression. So rate is equal to K times the concentration of nitrogen dioxide squared. So if you look at the net reaction or the net equation, we see that this is the rate law that is obtained for it. But it does not feature any carbon monoxide. That means any change in carbon monoxide concentration does not affect the rate of the reaction. As such, we say that it has a rate order of 0. But look, the rate law expression has NO2 to an exponent 2. That means doubling the concentration of nitrogen dioxide quadruples the rate of the reaction. So hold that for now. This here is the experimentally determined rate law for the net reaction. This is a very important piece of information here that I want you to grasp. Listen to this. In elementary reactions, the reaction rate is directly proportional to the concentration of each reactant, and each reactant has a rate order of 1. This is unlike the reactants in a net reaction, where the rate orders must be determined experimentally. For a point of emphasis, we'll go back to that net reaction or a net equation. To determine the rate orders of nitrogen dioxide and carbon monoxide, experiments had to be performed before one could have attained this rate law equation. However, when we are dealing with this reactant species in the elementary steps, a different ball game happens, because we are forming that this one is colliding with that one, all the species within them will have a rate order of 1. So this brings us to something that is called the molecularity of the reactants in the elementary reactions. So let us suppose an elementary reaction had only one species, A. It is said to be unimolecular, and it will have a rate law expression as K times A to the first power, as exemplified by an activated ozone molecule decomposing to give an oxygen molecule and this oxygen atom here. And its rate law expression will be equal to K times the concentration of ozone raised to a power of 1. We're just putting in that 1 there for a point of emphasis. If it has two species, for example 2 moles of A, it will have a molecularity is called bimolecular, and this will be its rate law expression. Specifically, if 2 nitrogen dioxide molecules are colliding to produce these species here, then the rate law expression will be K times the concentration of NO2 to an exponent 2. If it is A and B, it will also be bimolecular, but the rate law expression will be K times what these concentrations are, product of those. You have 2 of these and 1 of this, you're going to have, for example, like this, it is said to be thermolecular, and the rate law expression will be like this: A to an exponent 2, B to an exponent 1. Okay, you have 2 of these and only 1 of that. Specifically, if you're doing a bromine plus a bromine and an argon, it will be like this. So this is what is meant by the molecularity of the reactants. In these reaction mechanisms, one of the steps is said to be slow, and it is called the rate determining step. And the entire rate of the reaction depends on the rate at which that slow step is operated. Here's an analogy that I'm using for you to understand this concept. This is a conveyor belt that's spinning in that direction, and somewhere along the line here, bottles are filled with a certain product, and they approach a station where worker A is located. The job of worker A is to cap those bottles and send them to worker B, who places these bottles in boxes. After these boxes are filled, the conveyor belt takes them to D, where the worker there closes the boxes, tapes and labels them. After that, the boxes go to worker E, whose job is to take the boxes off the table and stack them on the floor. Worker F and his crew of workers are responsible for taking the boxes and placing them in a truck for delivery to consumers. The boss comes around and is furious. He sees a stack of boxes piled up on the floor here. Who is the person that is determining the rate at which the trucks are loaded and the products are delivered to customers? If you say F is the guy that is responsible for that, we will say that F and company constitute the slowest step in this whole process. Doesn't matter how quickly A caps the bottles, how quickly B puts them in the boxes, how quickly D tapes the boxes and labels them, how fast E puts the boxes on the floor. As long as this fellow here does not get the boxes placed in the truck so the truck can leave and deliver the goods, productivity will not be at the rate that is desired. So we can say that the slowest step is what is called the rate determining step. Similarly, in reaction mechanisms, one of the elementary steps is the slowest, and it is called the rate determining reaction or the rate determining step. As such, this step is used to calculate the rate of the net reaction. In this step, since it is slow, the activation energy of the reaction is highest. Reaction mechanisms are guided by the rate law equations that have been determined experimentally. Returning to a net reaction, As noted before, according to the rate law equation, the rate of the reaction is proportional to the concentration of NO2 raised to an exponent 2. This means that in the reaction mechanism, one of the steps that is made the slowest must have NO2 written twice, such that its rate equation is same as that for the experimentally determined equation. Let's unpack that a little bit. This is the experimentally determined rate law for the net reaction. This rate equation can also be derived by using the species present in the rate determining step. So if you want to create a reaction mechanism, one of the steps that you call the rate determining step must have this written twice. You see, look, you must have this written twice, because each of these will have a rate order of 1, it have a molecularity of 2, and the rate of this according to this elementary step will have this rate law equation, which is the same as this experimentally determined one. So what we're saying is that the experimentally determined rate law guides the creation of a reaction mechanism. Since this is the rate law equation, it's telling us, look, you must have 2 NO inside, because this is raised to an exponent 2. You have to put in one of those steps NO and another NO. It must not have any other species inside. There's some criteria that determine whether or not a reaction mechanism is valid, and there are 3 of them. 1, there must not be more than 3 reactants in any elementary step. The rate law equation for the rate determining step must be the same as that for the net reaction. And thirdly, the sum of the elementary steps must produce the net reaction or the net equation. Let us go and check our mechanism to see whether or not these 3 criteria have been fulfilled. First of all, we don't see any of these having more than 2 species. Number 1, if you were to take this rate determining step and have the expression for the rate law equation, since each of these, as we emphasized before, is having a rate order of 1, this will be its rate law equation, and it is the same as that for the experimentally determined rate law equation. Number 3, the sum of the elementary steps must produce the net equation. This one goes away, that one goes away. NO2 is same here, NO2 is same here. And when you add this guy plus this guy, that's all left there. You get this one here and that one here. So all 3 criteria have been fulfilled. If one were to sketch that in this energy profile diagram, you're going to see that the first step, which is called the rate determining step, will have a high energy of activation, and then the other one will be fast, because it has a relatively much lower energy of activation. So if you look at this reaction mechanism one more time, we'll call this a rate determining step, and that's slow, and obviously the other one will be fast. How would you describe this energy profile diagram? There's the first fast step with low energy of activation. This one is going to be a slow step here, high energy of activation, and here you're going to have another fast step here. And of course you're going to have 3 elementary steps. Which one here will be the rate determining step? That one there. We have some sample problems here that we will solve, such that our understanding of reaction mechanism is consolidated. Here is a reaction that involved nitrogen dioxide and fluorine gas to give this product here. Its experimentally determined rate law equation was found to be that. So if we can unpack that a little bit, we can see that it is force order with respect to nitrogen dioxide and also force order with respect to fluorine. The idea now is to propose a reaction mechanism for this reaction. Since the rate law equation is this. It means that the rate determining step of the reaction mechanism must have only this guy and that guy inside. Because each of these in the elementary reactions, that is going to have rate order of 1, that will have a rate order of 1. So when you do the rate law equation, it must turn out to be what that is. Listen to this. Reaction intermediates must not be included in the rate determining step, since intermediates are fleeting and they can't be used to measure rate. So one of the elementary step number 1 must involve the reaction of nitrogen dioxide and fluorine, and it of course must produce the product NO2F. But look, this is accounted for. 1 fluorine is there. So what do you think this one must be? It must be the other fluorine. This guy is not featured as a reactant. So what do you think we should call that? It is called a reactant intermediate. We are having only one NO2F there, but we need another NO2F here. Because when we add these equations, you must end up with 2 of them. Some things must be reacting to produce another of those guys. But this one here must be somewhere here. Alright? So what must you react that way to give you this? It must be another NO2. If we add these, what we get? You have 1 here, 1 here, so you end up with 2. This one is going to disappear. F2 is here, that is 1 there, and you have another one here. So you have that. Which one will be the rate determining step? Look at the experimentally determined rate law. It has NO2 and F inside. See one that has exactly only these 2 as reactants. It must be this equation here. We call that slow step, and of course, the other one must be called the fast step. Not a problem. So you're given a reaction mechanism for the decomposition of dinitrogen pentoxide, and you're asked to find the net equation. All you have to do is to add these 3 elementary steps and find the net equation. We have this one over this side here, and that one is there. This one here is present here, is present there, so we take these off. And NO is here, another one is here, and NO2 is here, and an NO2 is there. So you bring the one down here, we have this species here, we have 1 and 2, that gives you 3, and this oxygen stays here. But look what happens. We know that this is a reaction intermediate. We have an extra one over this side. So we need to double up this equation here such that we'll produce another species like this one over this side, and we can cancel up there. So the next thing is to modify this reaction mechanism. Let's look at the equation when we had only 1 more. You have 1 of this and 1 of that. If you put a 2 there, this gets 2 and 2. And this is your net equation. This is a very complex mechanism, so you're not going to delve much into it. Okay? You will just want to leave that as it is there. Problem number 3. The following are elementary steps for a reaction mechanism. Use them to deduce the net equation. Of course, we'll add them up together. This has 1 chlorine over this side, 1 chlorine over this side. They have 2 there, so chlorines go. This has 1 COCl here, 1 COCl here. Everything goes. So what we have? We're left with this. That's there. This one. And you are going to have this alone. So this is a net equation. Okay, I want to ask you some other questions. Which elementary step is most likely to be the rate determining step? Remember we said, right? We said that you can arrive at the rate law equation in 2 ways. 1, by carrying out experiments using the reactants in our net equation, or by using the species in the rate determining step. But whatever species we're using in the rate determining step, must be present in a net equation. We are going to look now at one of the elementary steps to see where either of these is present, or both of them. Not present here. Carbon monoxide is here, but we can't use this as a rate determining step because this is a reaction intermediate. The only one that's left has what is inside the net reaction is this one. So this step here must be the slow or rate determining step. So we say this one here, take it out, must be step one. What is the rate law equation for the reaction? We did not get any information about the experimentally determined rate law, but we know the rate determining step here. So what do you think should be the rate law equation? So the molecularity of that in the elementary step is unimolecular. So its rate law must be that. So what would these be? As long as one is slow, all the rest must be fast. And that's our sketch of the energy profile diagram for that reaction will be. First one is slow, these two are small activation energies, and that's what it is. Ozone reacts with nitrogen dioxide to form dinitrogen pentoxide and oxygen according to this equation here. So that is our net equation. You're given some more information here. The experimentally determined rate law is found to be this. So it has nitrogen dioxide to the exponent 1, ozone to the exponent 1. And the proposed reaction mechanism consists of these two elementary steps. One is indicating to us that a nitrogen dioxide molecule reacts with ozone to give you nitrate, an oxygen molecule, and then nitrate reacts with nitrogen dioxide to give you dinitrogen pentoxide in the other step. Is this mechanism valid? If so, what is the rate determining step? Look to see if all three criteria are fulfilled. Number one, we see whether or not the addition of the elementary steps produce the net equation. This here seems to be a reaction intermediate. It goes. You have a nitrogen dioxide here, one here, another one here, and you have an ozone there. Bring them down, bring them down. You get one of this here and one of that. Let's see if this is the same as the net equation. Exactly. As far as that is concerned, it is valid. But now we have to see whether or not the rate determining step as a rate law equation, which is the same as that obtained experimentally from the reaction between nitrogen dioxide and ozone. We have to look at an elementary step that has either one or both of these. Nitrogen dioxide and ozone, which one has it? This one has it. And of course, each of these will have a rate order of 1. That's something that's understood. So its rate law equation, of course, will be this, which is the same as that guy there. Sample problem 5. So these are 3 elementary steps that constitute a reaction mechanism for a certain reaction. You're asked to find what is the net equation for the reaction, which wouldn't be difficult to find. What do? We'll add these up together. What are the reaction intermediates? Those are the things that disappear, which is a slow step. And you're asked to sketch the energy profile diagram for the reaction. Adding all of those together, let's see how they did that. J goes, that will be a reaction intermediate. K goes, another reaction intermediate. What are we left with? We're left with G, 2 H's, and L. And they give N. So that's the equation there. Now, we'll have to look at which elementary step has some species that are present here, but not a reaction intermediate. And that is the one that we used to formulate the rate law equation. So you can see this is the one here. Doesn't necessarily have to involve this one here. So what is going to be the rate law for that? It's going to be g to the 1. Okay. Now you're having two h's, it becomes h squared. Let's see what it is. That's the rate law equation using this elementary step. So when you look at the net reaction, you can see that L will have zero rate order. And of course, the energy profile diagram for the reaction will look like this. I know that this has been very intriguing, and our understanding of this, you can see, was based on our profound understanding of rate laws and rate law equation. So I beseech you to watch the video again to consolidate your understanding. Thank you.